Hello guys, good evening. Can you hear me? Yeah, hi. Did you finish your assignment last class? Okay, this is your first class, Aditya.
Yes, sir. It's my first chem class. I did the physics class earlier. I watched the video of the part one of some concepts of chemistry.
Okay, so you have gone through the video, right?
Yes, sir.
Got it. So we have only discussed the basic things. Okay, so we'll start the next part today. Okay, this is the more important one. Okay. Yeah. So let all of you have joined. Like let them join, and then we'll start the session. So I hope all of you have finished the session finished the assignment of the last class. Okay, it was not much, around 20 odd questions were there. Okay, based on the law of combination. Okay. So the screen is visible now, correct? So the last class we have discussed about the average atomic mass also, right? How to find out the atomic mass of a substance if they have isotopes, correct? The formula we have seen last class. Okay. So let's try this question first. Write down. The question is carbon occurs in nature as a mixture of C12 and C13. The average atomic mass of carbon is 1,1. What is the percentage abundance of C12 in nature? Let's try this question. Yes, right. Oro, Priyam, correct. No, Oro, it's not that. You check your calculation, Oro. Correct, Pradyum. Priyam, you are also wrong. Check your calculation, both of you. No, that I told when we have all three, C12, C13, C14. And that was also not exactly 98.9. It is little less, but mostly it is that only. Okay, but that is there when we have three possible things, right? C12, C13, and C14. Try this. Yes, it is 98.9%. It is right. See, what happens, excuse me, the question is we have a carbon sample. Suppose we have carbon over here, right? And it has only two isotopes, that is C12 and C13, which is given in the question. We need to find out here that what is the percentage abundance of C12 if the average atomic mass is given 12.011. So what I assume this C12 as X out of 100. So this would be 100 minus X, right? So now if I write down this average atomic mass, the formula we have X by 100 into its atomic mass 12 plus 100 minus X by 100 into 13. So 12.011 is equals to 12x plus 100 minus x into 13 divided by 100. Now you just need to solve this. So that would be x equals to 1300 minus 12.01, sorry, 1201.1. That is 98.9. So percentage abundance of C12 is 98.9% and rest is C13 in that sample. No doubt. Correct. Now we'll try to understand the other concept in this chapter. Okay. Just give me 1 second. Okay. So the next concept we have to study is, and which is the most important one for this chapter and entire chemistry, that is mole. Could you tell me what is mole? How do we define mole? Anyone? Any idea about this term? What is a mole? Guys, can you hear me? Yeah. Okay. These many particles. Okay. Okay. See, how do we define a mole? Write down the definition of it. Okay. It is the amount of substance. Write down, all of you. It is the amount of substance which contains as many number of entities as there are number of atoms present in 12 gram of C12, that is carbon 12 atom. As many number of entities as there are number of entities present in 12 gram of C12 carbon atom. This is what the definition. The mole is what? Mole is nothing but the amount of substance. Right? It is nothing but the amount of substance. Correct? Like, you can understand this with an example of, like I said, if I take the example of 1 dozen. 1 dozen is what? 1 dozen is 12, right? 12 entities. You can take anything. 12 atom, 12 chair, 12 pen, 1 dozen bottle means 12 bottle, anything. So basically dozen means 12. Similarly, mole also signifies a number, right? Mole also signifies a number. And what is that number? That number is the number of atoms present in 12 gram of C12 atom, right? Now the first question is that how many atoms present in 12 gram of C12 atom, correct? Okay, so it has been experimentally observed that 12 gram of C12 atom, contains 6.022 into 10 to the power 23 atoms. This has been experimentally observed, right? 6.022 into 10 to the power 23 atoms, correct? So you must have done this in 10th grade also, right? There they must have given this 6.023, yes or no? It was 6.023, correct? Right, so that we have a difference in the third digit of this decimal, okay? So that won't make much difference into your answer, but from now onwards, we'll take 6.022 into 10 to the power 23. That only will take, right? Not 23 into 10 to the power 23, but it is 6.022, first 22 and then 23, right? 6.022 into 10 to the power 20. This number is observed by a scientist. This fact actually, which is experimentally determined. Okay, so this number has been determined experimentally. Right, and this has been observed by a scientist called Avogadro. Right, that's why this number we also call it as Avogadro number. Right, this number we also call it as Avogadro number, represented by n subscript a. This is Avogadro number. We'll use this symbol only for this particular number. Very important. Copy this down. Okay. Done, all of you? All of you have written this? Correct. So this is one thing. Now, 1 mole means what? Like I said, it is just a number. So like 1 dozen is 12 entities, can be anything. Right. Basically, dozen means 12. So 1 dozen means 12. Similarly, 1 mole means 6.022 into 10 to the power 23 entities. Okay, entities, correct? This is 1 mole. So like dozen is 12, so 1 mole is this. This is what we need to understand. Mole is nothing but a number, right? So this is one thing, correct? Now, this, as I said, this number is nothing but Avogadro number. So we represent this number by Na also, right? Na also. So if I write down 1 mole atom means what? How many atoms? Means we have Na atoms, right? Na atoms. Okay, 1 mole electrons, right? 1 mole electron means Na electrons. Okay, electron means Na electrons, right? So like I said, mole is just a number, right? So we have to specify the entities with it, then only it makes sense. Fine. One more information you must have, that 1 mole molecule also, if you write any gas, you can say. So 1 mole molecule is equals to, again, it is Na molecules. So basically what point I'm trying to make is what? That mole is just a number. So whenever you get this particular term, mole, you must think about this number, that is the Avogadro number. Oh, I'm sorry. molecules, correct? Okay. So this term is nothing but a number that you have to think. This is one thing. Now there is one, like there are three formulas basically to find out the number of moles based on the given data. Okay. Do you know those formulas? How do we find out number of moles? Any idea you have? Okay. Yeah. We can do that unitary methods that we can do, right? We can obviously do that. It is means most of the questions here in this chapter will be unitary method only. Okay, but you should know the formula also. That's why I'm writing it down. So formula for number of moles is equals to given mass divided by atomic mass. If atom is there, we'll take atomic mass. If molecule is there, then we take molecular mass. Okay. Another formula is number of entities divided by the Avogadro number, which is Na. Okay, if gaseous species is there, so the volume occupied by gas divided by the gas volume occupied by the gas at STP, that is 22.4 liter it is. Okay, but one change we have over here in this, that this formula is valid only at STP. Okay, at STP. What is STP? STP stands for standard temperature pressure. So standard temperature pressure means temperature must be 0 degrees Celsius, which is nothing but 273 Kelvin, and pressure is 1 atmospheric. One atmospheric. Done. Okay. Now you see, if you try to understand the first formula here, this one, right, you can easily understand this. Suppose we have, I'm taking one example. Suppose we have O2 gas, right? O2 molecule we have. So could you tell me for 1 mole of O2, what should be the mass we have? What should be the mass? Could you tell me? For 1 mole of O2? 32 gram, right? Because one oxygen atom is 16 grams, so we have 2, so it is 32 gram. Right? 32 gram. So 32 gram also is the molecular mass of O2. Right? So we can say 32 gram here. So we can say all molecular mass of the any molecules, that molecular mass is equals to 1 mole, right? So molecular mass or atomic mass of any substance signifies 1 mole. Is it right? Right? So for any substance, any molecule, if you have taken the molecular mass of this, means you have taken 1 mole of that substance. Okay. Could you understand this second formula? It is something like this. Suppose you have taken 24 pen, and if I ask you how many dozen you have, you'll say 2 dozen, right? 2 dozen. So what do you do? You'll take the number of entities divided by 12, which is equals to 1 dozen. That is what we have done here. Number of entities divided by the Avogadro number, which is the 1 mole basically. So this is nothing but the number of moles. Now this formula, volume occupied by the gas divided by 22.4 liter. We'll try to understand this one now. Okay, but one thing you must understand here, for the third formula that I have written, it is important. And third formula that I have written here, it is applicable only for gases. Write down. This is applicable only for gases. Only for gases, right? We cannot use this for any solid substance. Okay, volume occupied by the gas divided by 22.4 liter. Okay, now why this is 22.4 liter we are using here, that we'll try to understand. Okay, any confusion, any doubt till now? All of you, please respond. If not, then you can type CLR. Okay. Now you see, there is a equation. There is a equation, and we call it as equation of state. Have you heard about it? Equation of state. And this equation of state, we write only for gases. Okay. And what is that equation? That equation is PV is equals to nRT. PV is equals to nRT. This is the equation of state, we call it as. Have you seen this equation? Ideal gas equation. Okay. Can I go a little bit of depth of it? If you want to know, because we'll discuss this again in states of matter. But if you want to have some understanding of this equation, I can discuss that also. Okay. See, actually what happens, how do we define the position of any object? That you tell me. If I ask you to define the position of any object, how do you define that? We mainly have a coordinate system, right? Yes or no? We mainly have a coordinate system where we define the position of an object. Suppose the object is here, right? The object is here. Then if the coordinate of this point, if I write, suppose it is 3, 4, 2, this means what? What do you understand by this particular thing? This means that this point you can achieve, you can reach to this point from this is the zero, the origin that you have from your start. So you have to go 4, this is x coordinate, this is the y coordinate. So you have to go 4 unit distance in x direction, and then 2 unit distance into the y direction. You will get the coordinate, right? You'll get the point. That is how we define the position of any object, right? Even if you see all these missile technology that we have, there we specify the target with this coordinate system only. We'll fix the coordinate into the computer, right? And then the missile attacks on that particular location. So this is how we locate the position of any object or any target. Correct? Understood? Right? You know this coordinate system? 4, 2, you have the understanding of that, right? Right, Anusha, coordinates, right? So similarly, for gaseous particle also, if you want to locate the gaseous particle, so we also use different variables for specify the position of gaseous particle. Okay, what we use variables to specify the position of gaseous particles. Here for this object, what are the variables we have? X and Y. Okay, the distance that we have. Okay, similarly, for gaseous particles, we also use some variables, and those variables are pressure, volume, and temperature. These 3 variables we have. Okay, so for gaseous particles, we use these variables to specify the position. Suppose the gaseous particle is here, right? So at this point, we must have, suppose this point is A. So at this point, we have a particular pressure, a particular volume, a particular temperature, right? That is, suppose PA, VA, and TA. This is pressure, volume, and temperature at this point. At another point, suppose we have some point over here, B. Here we have different pressure. Aditya Raj, if you can, if you can make it, if you can join the session, after some time, then it would be best for you to be in the session. Okay. Anyways, you can watch the recording later. Okay. But I would suggest, if it is possible, try to be in the session. Okay. If you can manage with your, internet issue and other things. But anyways, I'll share the recording with you. But I'll suggest to, try to be in the session. Fine. So at point B, the pressure, volume, and temperature is PV, VB, and T. Okay. So any one of these variable changes, we say that the position of gas is changing. Any one. Are you getting it, guys, all of you? We can have same volume, we can have same pressure. Suppose if we take at this point, suppose this is pressure volume coordinate we have. So suppose at this point we have same volume. This point we have same volume on this line. This point we have same pressure. This point you have same pressure. If it is pressure, it is volume. Yes, it is like X, Y, Z coordinate. Okay, at a given temperature, we define like this. So position of any gas is defined by these 3 variables. That is the point I'm trying to make. Okay, what can be changed, what cannot be changed. Okay, what should be constant and other things. That all permutation and combination you can apply. That is possible here, right? But the position of any gaseous species is defined by these 3 variables. Are you getting it? Correct. Now, the second point, what I said, that any one of these variable, if it is changing, any one variable, if it is changing, it means the position of gas is changing. Right on this point, the position of any gaseous particle, write down the position of any gaseous particle is defined by any gaseous particle is defined by the variable which is pressure, volume, and temperature. Pressure, volume, and temperature. Okay, next line. The next line, the change in any of these variables, the change in any of these variables, in bracket you write down one or more, the change in any of these variables, in bracket you write down one or more, one or more, bracket close, indicates the change in position of the gas. Indicates the change in position of the gas. Is it clear? Okay, fine. Now the next point you see, if you have to establish a relation among these three variables, P, V, and T, right? If you have to establish a relation among these three variables, P, V, and T, for a given amount of gas, okay? So for the relation of these three variables, for a given amount of gas, is this one, that is P into V is equals to N R T. This is the relation we have, and we also call it as equation of state. You see the heading, equation of state, means at one particular state the gas holds this equation for a given amount of gas. Whenever I say amount of gas, right, it means I'm talking about moles of gas, or I'm talking about mass of gas, volume of gas, etc. Mainly amount is mostly considered. Is it clear? So at this point of time, at this point A, for a given amount of gas, the relation of PV and T, we can write down with this, PV is equals to nRT. We can also derive this relation, but I am not doing that. We'll discuss that in gaseous state, okay? Where, yeah, I'm coming to that, Shirish, just a second. Where this R is, this R we call it as universal gas constant. Universal gas constant. N is the number of moles, amount of gas basically. The number of moles, which means the amount of gas, right? R, like I said, is a universal gas constant, right? And the value of R is 8.314, sorry, 8.314 joule per mole Kelvin. You must remember this value, okay? We'll be using this in entire physical chemistry, okay? 8.314 joule per mole Kelvin, or the another unit is 0.0821 liter ATM per mole Kelvin. Got it? So this is the equation of state. Any doubt? No? No doubt, guys? Clear? Now, why we have discussed this? Yes, pressure into volume is nothing but energy. PV is the work done. We'll discuss that later. Okay. So hold on for some time. Okay, we'll discuss that later. But pressure into volume is energy. It is a work done. Pressure, volume, work done. Right? So we'll discuss that later. Don't compare the energy thing over here. Okay. We cannot discuss everything in one particular chapter. Okay, but still let it be. So why we have discussed this? We have discussed this in order to understand this formula, correct? This was the objective, right? This was the objective. And in order to understand this formula, we have discussed this. This is the equation of state, only applicable for gas, right? Only applicable for gas. Now you see what happens if I ask you to find out, calculate one simple question, calculate the volume occupied by the gas by the 1 mole of gas. You write down by 1 mole of gas at STP. Could you find out this? Could you find out this? Did you find out this or you know this? Yes. So you must have done this in 10th standard also. So what I'm telling you, if we know the relation of PV, right, we can write down this relation and we can calculate volume, right? So the relation is PV is equals to nRT, right? So this V we need to find out, right? Volume, number of moles is 1. What is R value? R value will take 0.0821. Temperature is STP. So temperature is Kelvin. We always write down temperature in this equation in Kelvin, right? 273 Kelvin. Pressure is 1 atmospheric, right? So when you solve this, you'll get 22.4 liter. So this means what? I know all of you know this particular thing. This means what? When the condition is STP, so what we can say, at STP, the volume occupied by 1 mole of gas is 22.4 liter. Hence, the formula we have is number of moles is equals to the volume occupied by the gas divided by 22.4 liter, but this is only applicable at STP, right? So whatever the volume occupied by the gas at STP, that divided by 22.4 liter gives you the volume. Now 8.314 we won't use here, because you see why we do not use 8.314, since we need to find out volume, correct? We need to find out volume. So if you use this unit, see what happens here. Try to find out the unit over here. I'll write down just a second. See, this 1 mole, right? So if I write down the unit here, you see this is mole. So I'll write down the unit mole. I'll write down the unit mole. What is the unit of this? Liter ATM per mole Kelvin into, this is temperature, Kelvin. What is 1 in the denominator? It is ATM, because the pressure is 1 atmosphere. So when you solve this, you see this ATM gets cancelled, Kelvin gets cancelled, mole gets cancelled, and means this term is nothing but liter. That's why we have used this particular value. Yes, work done is liter ATM. Because you need to find out volume, right? You need to find out volume. You can use 8.314, but then again you have to convert that into a liter ATM. Joule, 8.314 joule. Joule is the energy, right? But volume, for volume, you must have to write down this in liter ATM. So that the volume, the unit of volume is what? You get liter over. And since we have to find out volume in liter, so I have directly used 0.0821 liter ATM mole per Kelvin. You see the unit we are getting liter only. Generally 8.314 we use in thermodynamics, where we deals with energy. Okay, here we are not dealing with energy, right? We are dealing with amount, volume occupied. Okay, we are not dealing with energy. Energy related calculation we are not doing here. However, pressure into volume, the product is energy only. But that is not our concern. Clear? Any doubt? So since 1 mole of any gaseous species occupy 22.4 liter at STP, that's why the formula we have. Any doubt? No? Okay. Solve this question. Write down out of 5 moles of CO2, 10 to the power 23 molecules have been removed, calculate the number of moles of CO2 left. Try this. Are you done? 1.84. No, it's not correct, Anusha. You can take approximation. You can take 6.022 as 6. 4.8 approximately. Yeah, that's right, Shitish. Okay. See, what we have to do here. The question is, we have CO2 gas, right? We have a sample of CO2. And 5 moles of this we have. And out of this 5 moles, we have removed what? These many molecules, 10 to the power 23 molecules we have removed. Now what you have to find out, how many moles of CO2 left? Okay, how many moles of CO2 left? So obviously you see here we have moles, here we have molecules. So we cannot, subtract this moles and molecules together. Either you have to convert this molecules into moles or this moles into molecules. Okay. So since the answer we need to find out in terms of mole only, so what I'll do to get the answer in one single step, what we'll do, we'll convert this molecules into the number of moles. Okay, so these many molecules is equals to how many moles? We can find out this as 10 to the power 23 divided by Na. This is the moles, right? The second formula that we have, okay, number of entities divided by the Avogadro number. Okay, further we can solve this as 10 to the power 23, and for the calculation I am taking here 6 into 10 to the power 23. Okay, you can take 6.022 also, but this kind of approximation you can make. Okay, so this means what? It is equals to 1 by 6 moles. This means what? Out of 5 moles, 1 by 6 moles we have been removed. Then how many moles left? Number of moles left, 5 minus 1 by 6, that will be 29 by 6, 4.83 moles. This is the answer for this question. Clear? Understood all of you? This one you see? Out of 5 moles of ozone, out of 5 moles of ozone, 3 moles of O2 are removed. Calculate the number of moles. Calculate the number of moles of oxygen atom left. This is the question. Try this now. Try this. No, it's not 9, Kshitish. Tell me the answer. Oro, Pradyun, Anusha. It's not 12. Wrong, Oishik. It's not 4.5. No, it's not that, Anusha. Anusha, check your calculation. Yes, Pradyum, that is right. No, Ashish. See, actually, the question is calculate the number of moles of oxygen atom left. First of all, could you tell me what is the formula of ozone? Nine moles, that's right. That's right, Oshik. First of all, you see, ozone is, I'll do this way. Ozone is O3 molecule and this is oxygen O2. So we have initially 5 moles of O3. This means 5 into 3, we have 15 moles of oxygen atom in this. Because one molecule has 3 oxygen atoms. So 5 mole molecules means 5 into 3, 15 moles of oxygen atom. And out of this, what we have removed? We have removed 3 moles of O2. Means we have removed 6 moles of oxygen atom. Right? So the number of moles of oxygen atom left, that is equals to what? 15 minus 6 means 9 moles of oxygen atom left. Hence the answer is what? 9 moles. Or we can also write 9 into Na. This is the answer for this question. You said only 9, it's not 9 moles. Acha, question itself is number of moles. It's fine then. Okay. Yeah, shit is fine. No issue. correct? So 9 moles of oxygen atom left. When you write 9 into Na, what does it mean? What do you mean by 9 into Na? 9 mole of that substance. So if the question is how many oxygen atom left, then how many oxygen atom left? 9 into Avogadro number, right? This means 9 into Na, this atom left into this. Okay, right. One more question we'll see. It's a very simple one. Basic concepts. I'm trying to understand, to make you understand the basic concepts of it. Okay. The question is how many molecules of water and oxygen. Read out the question properly. How many molecules of water and how many molecules of water and oxygen atom, right? So molecules of water and oxygen atoms are present in 0.9 gram of water. Try this. So 0.05 mole what, Pradyun? Okay. Okay, fine. You see, first of all, if I ask you, what is the number of moles of water? That is given mass divided by molecular mass of water is 18. So it is 0.05 moles. Yes. So we know 1 mole is equals to Na molecules. 1 mole is equals to Na molecules. 1 mole of H2O means we have Na molecules of H2O. Right? Now you see water is H2O. So in one of this molecule, we have 1 oxygen atom and 2 hydrogen atom. We need to find out the number of molecules of water and number of oxygen atom. So if you know the number of molecules of water, we can multiply that with 1 and that will become the number of oxygen atom, because 1 mole of water has 1 oxygen atom, right? So number of molecules of water is equals to of water is equals to 1 mole is Na, 0.05 mole is 0.05 into Na molecules of water. And number of molecules of water is the number of oxygen atom, because one molecule oxygen atom, because one molecule of water has 1 oxygen atom. So these many molecules of water has these many atoms of oxygen. Okay. If I ask you, this was a question. If I ask you, what is the number of hydrogen atom? What is the answer? Number of hydrogen atom in this 0.9 gram of sample. So one molecule of water has 2 hydrogen atoms. So obviously these many molecules of water has 0.05 into 2 Na atoms. So that would be 0.1 Na hydrogen atom. So did you understand? Did you understand the concept of atoms, molecules calculation? Right? One more C. If I ask you one more question into this, the number of electrons in this, number of electrons present in this sample means 0.9 gram of water has how many electrons? Will you tell me? Point 0.5 Na electrons. Okay. So could you tell me in one molecule how many electrons we have? I don't know. I don't know. Like that's what I got the answer from your side. Okay, we'll see what is the answer we get. Could you tell me how many electrons in one molecule of water we have? This molecule, how many electrons? So electrons is equals to the number of protons, and protons is nothing but the atomic number. So atomic number of oxygen is 8 and hydrogen is 1, so 1 into 2, 2. So there are 10 electrons in one molecule of water. Is it clear? 10 electrons in one molecule of water. How many such molecules we have? We have this many molecules. So the number of electrons will be what? Into Na, number of molecules into the number of electrons present in one molecule. So that would be 0.5 into Na. This is the number of electrons. Did you get it? Any doubt? All of you understood? You can type CLR quickly. Okay, so they can ask you any questions regarding this: moles, atoms, electrons, molecules, anything. Basically, if you know the number of moles, you can find out all these things. Just these are the unitary methods, nothing much. Okay, what you need to know? You need to know how to calculate the number of moles. Okay, those three formulas. Based on the given data, you can use any one of the formula and get the answer. Okay. What ions? How? Means ions you can take, then the number of ions means you should have some ions present, like suppose we have N3 minus if they ask. So the number of moles of this into Na, that would be the ions. Ions and molecules, there is no difference. If they ask you the number of electrons in this, then N3 minus how many electrons we have into this one? See, Kshitij, what I said, that in ions and molecules, there is no difference, right? Only in the question, instead of molecules, you'll have one ions. Just you find out number of moles, that number of moles into Na gives you the number of ions. Simple, not more. But yes, if they ask you the number of electrons, then you have to see what ions it is, whether it is anion or cation. Like you see N3 minus if I write, so this N3 minus ion has 10 electrons. So in this case, the number of electrons will be 10 into the number of such ions. Get it? No doubt? Fine. Next, write down gram atomic mass. What is this gram atomic mass? The mass of an atom when expressed in gram. That is what it is, right? That is what you have studied. The mass of an atom when expressed in gram, it is known as gram atomic mass. Yes? Correct? But that definition we are not going to use now. In fact, that is not the correct way to understand the concept. Okay. Whatever you have studied till 10th, that you let it be now. The actual definition of this we have to understand. That is gram atomic mass. Write down the definition. It is the mass of one mole of an atom. Okay. It is a mass of 1 mole of an atom. Now, if I ask you, what is the mass of carbon atom? Mass of 1 carbon atom. What is your answer? Mass of one carbon atom is 12 AMU, right? Atomic mass unit. That is what we say. We don't say 12 gram. 12 gram is not the atomic mass of carbon. The atomic mass of carbon is 12 AMU, not gram. Okay, one thing. Now, if I find out the absolute mass of this, means if I convert this AMU into gram, that will be 12 into 1.66 into 10 to the power minus 23 gram. Just we convert AMU into gram. 1 AMU is this, so we multiply it by this into this. Correct? Right? Now the definition of gram atomic mass is what? It is a mass of 1 mole of an atom. So mass of one carbon atom is this. What is the mass of 1 mole of carbon atom? That will be 12 into 1 mole means Avogadro number Na. Correct? So Na, if I substitute here, we can write this as this is the gram atomic mass. Mass of 1 mole of a carbon atom, the definition is this. Gram atomic mass is nothing but the mass of 1 mole of an atom. So mass of 1 mole of an atom, carbon atom is this. Now when you multiply this, coincidentally what happens, this product is coming out to be 1, correct? And hence the mass is 12 gram, because the unit here is gram only, 12 gram. And since the mass here is coming out to be 12, then what we say, that's why we said that if the atomic mass of an atom, which is 12 AMU, is expressed in terms of gram, then it is gram atomic mass. But that is not the definition. Definition is what? Mass of 1 mole of an atom is the gram atomic mass. Since coincidentally 12 AMU becomes 12 gram, that's why the definition is given in your book in 10th standard, that if it is expressed in gram, it becomes a gram atomic mass. So what is the difference here? Difference is that if somebody asks you what is the atomic mass of carbon, the answer should be 12 AMU. What is the gram atomic mass? It is 12 gram, not AMU. Right? But for calculation, we say, okay, atomic mass is 12 gram only. This we use for our calculation. We don't, use the gram atomic mass. We don't say like this, the gram atomic mass of carbon is 12 gram, right? So for calculation purpose and other things, we consider atomic mass as gram atomic mass only, but there is a technical difference between the two. Molar mass, only the difference is we do not have atom there, but we have molecule. So gram atomic mass becomes gram molecular mass there. Did you understand this? So if I ask you in other way, the gram atomic mass of any atom contains how many atoms? What is your answer? The gram atomic mass of any atoms contains how many atoms? That is the Avogadro number, because the gram atomic mass is the mass of any atom. So that's why this point you write down the next line. This point you write down. Gram atomic mass. One more thing I would like, I write down here. Gram atomic mass, we also call it as gram atom simply. So gram atomic mass or gram atom are same thing. Both are same thing. Don't get confused, right? So write down this note here. The gram atomic mass or gram atom of every element
the gram atomic mass or gram atom of every element consists equal number of atoms right of every element consists equal number of atoms, and this number is called Avogadro number. Okay, and this number is called Avogadro number. Did you write? Finished? Finished? Next line, write down. It can also be defined as write down. It can also be defined as the absolute mass of it can also be defined as absolute mass of any atoms, Avogadro number. Okay, it can also be defined as any atoms of any element. Finished? Should I repeat it again? It can also be defined as the absolute mass of any atoms of any element. Absolute mass is nothing but the mass in gram, not in AMU. Mass in gram. Okay, can I move on? Did you finish? Okay. Now, like this only, the similar kind of definition we have for gram molecular mass. Gram molecular mass. Okay. Write down, it is the mass of Na molecules. Mass of Na molecules or 1 mole of molecule. It is exactly same to the previous one. The only thing is, instead of atom, we have molecule, right? So write down, it is the mass of Na molecules. Okay, so suppose, for example, I have taken H2SO4. Could you tell me the molecular mass of this H2SO4? What is the molecular mass? Tell me, guys. Again, Anusha, you see, the molecular mass is 98 AMU, not gram. 98 AMU. So if I convert this into gram, the absolute mass is what? 98 into 1.66, 10 to the power minus 23 gram. This is the absolute mass, right? Hence, the mass of Na such molecules is equals to what? 98 into 1.66, 10 to the power 23 into 6.022 into 10 to the power 23. This product again becomes 1, and hence the gram molecular mass becomes 98 gram. Okay. Now you see, one gaseous law we are going to discuss, and that we call it as Avogadros law. Avogadros law. Avogadros law, it is defined only for gases. Only for gases, okay? The condition for this is we must have constant temperature and pressure. This is the condition. Constant temperature and pressure. Without constant temperature and pressure, this law you cannot apply. Okay? Write down the statement. Write down the statement. At a fixed temperature and pressure, write down at a fixed temperature and pressure, the volume occupied by a gas at a fixed temperature and pressure, the volume occupied by a gas is directly proportional to the amount of gas present. Right? Again, I'm repeating this. At a fixed temperature and pressure, the volume occupied by a gas is directly proportional to the amount of gas present. All of you have written? Yes, Shitish. So according to this law, the relation we have brought, that volume of gaseous species is directly proportional to its number of moles. More amount of gas, more volume it occupies. Okay. This we can derive with the ideal gas law, that is PV is equals to nRT. Just now we have discussed this. You see this relation here. PV is equals to nRT we have. So like I said, the condition is what? The condition is that the pressure and temperature must be constant, right? Pressure and temperature is constant. R is already a constant, right? So at constant temperature and pressure, what we can say? The volume and number of moles are directly proportional, right? Understood? So what we can say here, you see, the next thing is we can write V by N, volume divided by number of moles, is equals to constant. Constant. Right? So what we can write for any gas, at two different condition, just a second. So we can write here V1 by N1 is equals to V2 by N2. Okay, V1 by N1 is equals to V2 by N2. Means if you take two different amount of a gas at the same condition, so this is the relation we have. So what is N1 and N2 here? Could you tell me? What is N1 and N2? Moles, right? So what we can write here further, you see, could we write N1 is equals to the mass of the gas, which is M1, divided by the molecular mass of the gas. So this is the molecular mass. And similarly, N2 we can write M2 divided by the molecular mass of the gas. Since the gas is same, so molecular mass will also be same, right? Because we have same gas at two different conditions, right? Means different amount of gas at the same condition we are taking, right? So this relation is true. If I substitute this here, right, it becomes V1 by M1 is equals to V2 by M2. This is also, we can write this. Is it clear? See what I said. Suppose you have taken hydrogen gas, right? H2 gas. So you can take different amount, no? Suppose you have taken 10 gram and 20 gram. So 10 gram will occupy a certain volume, 20 gram will occupy a certain volume. But both this mass of the same gas, you have taken at two different conditions. Right? Sorry, not two different conditions. We have the same pressure and temperature, P and T are same. And we have taken two different amount of gas. I have taken M1 and M2 of the same gas, right? 10 gram and 20 gram. So M1 will occupy volume V1, M2 will occupy volume V2. So from this, we can also write down here this relation, because N1 is nothing but M1 by molar mass of the gas. N2 is nothing but M2 by molar mass of the gas, like this. So this N1 and N2, if I substitute in terms of mass, we'll get this relation. Correct? Right? Now what happens here, you see, this relation you see here, this one. If I have equal volume, if you have equal volume of two different gases at the same temperature and pressure. So when volume is equal, it means they have equal number of moles, right? Equal number of moles means equal number of molecules. So Avogadro law, we can also define this way. The statement, the one statement we have already discussed. The other statement we have, you write down here. Equal volume of all gases will have equal volume of all gases will have equal number of molecules at the same temperature and pressure. Right? Equal volume of all gas will have equal number of molecules at the same temperature and pressure. Right? One more statement we have for this. Okay. But before going into that, we'll understand molar volume. Okay. So write down the point here, molar volume. Molar volume is represented by Vm. Write down the statement of this. What is molar volume? It is a volume occupied by it is a volume occupied by 1 mole of an ideal gas. It is a volume occupied by 1 mole of an ideal gas at STP. Wait, Anusha. So molar volume definition you have written, it is a volume of an ideal gas, right? It is the volume of 1 mole of an ideal gas. Okay. For molar volume, the condition is not there. It is just the volume of 1 mole of an ideal gas. Okay. If you have written STP there, just remove that. Okay. Ideal gas is the gas which obeys PV is equals to nRT, this equation, which follows this equation, right? That is the definition of ideal gas. All gases which follows this particular equation, PV is equals to nRT, are called ideal gas. However, none of the gases are ideal gas. Ideal gas are perfect gas, basically. Right. Again, we'll discuss this in states of matter, gaseous state. Okay, so again, you let it be here. Right. So molar volume is the volume occupied by 1 mole of gas. So what is the volume of Vm? What is the value of Vm at STP? Could you tell me? Vm at STP. What is this value? Yes. This we have already calculated, 22.4 liter. Yes or no? Vm at STP. Standard temperature pressure. We'll substitute here. N is 1 mole. We'll get Vm is equals to this. Right? Another thing, this is the volume of 1 mole. 1 mole means how many molecules? 1 mole means how many molecules? Na. So can we say this is the volume of Na molecules? Vm is the volume of Na molecules, right? So next line you write down, equal volume write down like this. The next line write down, the molar volume of all gases, the molar volume of all gases will have equal number of molecules. The molar volume of all gases will have equal number of molecules, and this number is nothing but the Avogadro number. At constant temperature and pressure, that condition is always there, right? So molar volume of all gases will have equal number of molecules at constant temperature and pressure, and this number is the Avogadro number. Any doubt in these three statements that we have done? No doubt. Correct. So what all things we have discussed here. First of all, Avogadro's law is for constant temperature and pressure, and we have seen that the volume and number of moles is directly proportional. Further, we can write at a given condition for two different amount of gases, V1 by N1 is equals to V2 by N2. So if V1 and V2 are equal, the gases will have equal number of moles. Equal number of moles will have equal number of molecules, right? So equal volume gives equal number of molecules at constant temperature and pressure, right? Now, if these volumes are equal and that volume is equals to the molar volume, which is the volume of 1 mole, then obviously the number of molecules will also be equal, but that molecule, the number of molecule is nothing but the Avogadro number. For a non-ideal gas, we have different gaseous laws. We have different equation that we call it as van der Waals equation, right? And we are assuming that ideal gas, the concept of ideal gas is a hypothetical concept. Okay, we have given certain rules, and we say all those gases which follows these rules are called ideal gases. Okay, but practically none of the gases are ideal. Okay, that is a hypothetical concept. Okay, so we'll discuss that in detail, like those things, gaseous laws and all. We'll discuss those things in detail in gaseous state. Done? Okay. Now we solve two questions on this. I'll write down the question and you try to solve this. You must copy down the question also, because once you revise before the exam, you should have question with you. Write down a cylinder with a movable piston contains 2 grams of helium. 2 grams of helium at room temperature. Room temperature. More helium was added to the cylinder and the volume adjusted so that the gas pressure remains the same. Now you have to find out how many grams of helium were added to the cylinder if the volume changed from 3 liter from 2 liter to 2.70 liter. This is the question. Try to do this. Okay, 0.7 gram. So what we can do, we can directly use Avogadro law. V1 by M1 is equals to V2 by M2, right? So volume initially it is 2, mass is 2, and volume initially is, final is 2.7, mass we need to find. So M2 we are getting 2.70 gram. This is the total mass when we add helium into it. So what is the mass added? Because the question is the grams of helium were added. So mass added is equals to final minus initial, that is 0.70 gram. Okay, again remember here one thing, that it is not directly given that volume, that the pressure and temperature is constant here. It is not directly given, but it is given what? That at room temperature, right? And more helium was added to the cylinder and adjusted so that the gas pressure remains the same, right? So that's why we can apply the Avogadro's law here. Okay, this was the simple one. One more question you see here. from 44.8 liter of NH3 gas five into 10 to the power 23 molecules have been removed. Calculate the volume of NH3 left at STP. Options also given. Unit is liter here, you see. Try this. Yes, it was, Oro. Okay, so are you getting B? Tell me the answer. Okay, yeah, D is correct. See, first of all, initially what we can do, we can find out the volume, N1. It is a volume occupied divided by the volume at STP 22.4. So 2 moles initially present, right? Number of moles left is what? N2 is equals to 2 moles was present, and 5 into 10 to the power 23 divided by 6 into 10 to the power 23 has been removed. These many moles. So we are left with 7 by 6 moles. So we can write V1 by N1 is equals to V2 by N2. So V1 is 44.8, N1 is 2. So it is 22.4 is equals to V2, we need to find out, N2 is 7 by 6. So V2 is equals to 22.4 into 7/6. So answer is approximately we get 26.2 liter. Clear? Understood? So was this calculation tough? No. But actually, you see, now you listen to me, all of you, very carefully. Actually, what happens, we do not have to do all these things here. Even you do not have to put your pen down to solve this question. See what happens, we are removing molecules. Then volume should increase or decrease? Tell me. The volume should increase or decrease? Right? The volume should increase or decrease? Right? The volume should decrease. Correct. So that's why you see all the options you see, A, B, and C, it is more than this. Then none of the option is true, A, B, and C. The only one option is, that is D. You do not have to solve it. Are you getting it? Obviously, when you are removing molecules, so number of moles decreasing, so the volume occupied by the gaseous molecule is also less. That's why the only one option left is this 26 point. Sometimes what happens that they'll give you this kind of question with this option, and this calculation is really tough. Okay, calculation will be really tough, so that you waste your time in this calculation, right? So you understand this, there are more than 15 lakh students appear for the exam, right? Any competitive exam you see, this is the number we have, right? JEE, NEET, or any other competitive exam you see. Out of this 15 lakh, they are maximum, they are going to select 50,000. They are going to select it. You are not going to get good seats with this rank, okay? If you are not under 7, 8, or 10K, you won't get into good NITs, okay? There are other options, but still under 10K, you can think about some NITs or some new IITs that has been opened, right? So you see, out of 15 lakh, they have to select this 50,000 students, right? So obviously they do not select the students, but they reject the students. Rejection is always easier than selection. Okay, so always keep that in mind, that they'll frame this kind of questions so that you can waste your time, and eventually you'll be able to solve less number of questions and you won't qualify in the exam. All these, understanding you must, develop when you solve questions. Okay, it is not like the formula, then you put down everything and just you're calculating this, multiplying and dividing all these stuffs. Okay, that won't help you. Okay, so understood this point, all of you guys? Right, so you don't have to solve this question. It was direct option D. Yes, better if you are not, if you are putting 2, 3, 4 minutes for one question, better you should leave it. Okay, if you're stuck in the calculation, better you should leave those questions, and those questions you can attempt in the last 10, 15 minutes when you have done with all the paper. Okay, the only things that you can do some calculation in the last 15, 20 minutes. So those kind of questions which takes a lot of time, this is the expression we get and we need to just multiply and divide it to get the answer. If it is very tough, leave it for the last 15, 20 minutes. Okay, that is the best strategy. Understood? Okay, fine. The another term here that we are going to study is density. What is density? Represented by small d or rho. It is rho, the Greek letter rho. And we know density is the ratio of mass and volume. It is mass per unit volume, right? We all know this. Unit of density is, since it is mass per unit volume, so it is kg per meter cube, right? We can have gram per ml also. ml is nothing but cubic centimeter. So gram per centimeter cube also we can write, right? 1 kg per meter cube, this conversion you must know. 1 kg per meter cube is equals to 10 to the power minus 3 gram per ml. You can easily convert this. You should know this conversion, gram per ml. We also know 1 meter cube is equals to 1000 liter. 1 meter cube is 1000 liter. 1 ml is nothing but 1 centimeter. So both are the same. So this is the unit of density. Now there is a term we call, there's a term and we call it as, absolute, vapor density. Okay. VD, vapor density. Write down. It is the density of any gas. Vapor density, write down. It is the density of any gas with respect to the density of hydrogen. Okay. Density of any gas with respect to the density of hydrogen. Okay. Now, VD is equals to the absolute density of a gas, divided by the absolute density of hydrogen gas, H2. Means the density of any gas with respect to H2, if you calculate, that ratio is vapor density. Obviously, you see it is density by density. So vapor density is what? Vapor density is unitless. There is no unit for vapor density. Correct? Now, we can easily find out the expression for this, and we are calculating this with the help of PV is equals to nRT. Further, you see pressure into volume, N is moles, and that we can write mass divided by the molecular mass into RT. Right? Now you see, we are just doing some, change in this expression. We can write P into the molecular mass of the gas is equals to mass by volume into RT. Now you see this mass by volume is nothing but what? It is the density. So we can write density is equals to D is equals to P into molecular mass of the gas divided by RT. So this becomes the formula of this density. Did you get this? Okay. Just a second, guys. Okay, so we have this. Now we use this relation only to find out this formula of vapor density. So you see in the next step what we can write. The vapor density is equals to we have absolute density of a gas, which we can write P into molecular mass of the gas divided by RT, and this whole thing is divided by the absolute density of hydrogen gas molecular mass of H2 into RT. Correct? So what happens, this pressure gets cancelled, this RT gets cancelled. So further we can write this as molecular mass of gas divided by, for hydrogen it is 2. So the molecular mass of any gas is equals to 2 into the vapor density. Okay. So sometimes what happens in the question, they won't mention the gas, okay, or there will be mixture of gases, right? So to find out moles and other things, we must know the molecular mass of the gas, right? But they do not mention the gas, right? They do not give the molecular mass of the gas, but they gives us the vapor density of the gas. So once we know the vapor density, we can find out the molecular mass of the gas multiplying this by 2. So this formula is very important. Understood? One thing. The another thing you see, and that is the average molecular mass. The average molecular mass. This average molecular mass mainly we take, or this defined for a mixture of non-reacting gases. Mixture of non-reacting gases. And the formula for this is M average is equals to total mass of the mixture divided by the total number of moles. This means what? Suppose you have a mixture of gases, right? Mixture of non-reacting gases. We have a system in which we have mixture of non-reacting gases whose mass is M1, M2, M3, and so on. These are the three gases whose mass is M1, M2, and M3 present into this. And this mixture is what we are assuming it is non-reacting. So this M1 mass, right? So for M1, small m1, the molecular mass is capital M1. Small m2, the molecular mass is capital M2. Small m3, the capital mass is capital M3. Molecular mass. Right? So this formula becomes for three different gases of non-reacting gases here. Total mass is M1 plus M2 plus M3 divided by M1 by M1 plus M2 by M2 plus M3 by, this is the average molecular mass here. Done? Where this capital M is the molecular mass, small m is the mass. In doubt, guys, understood this? Okay. Now, we'll see one question based on this and then we'll take a break. Okay, so before the break, this is the last question. Write down the question. If the vapor density Vd of a mixture of NO2 and N2O4. See, one more thing, when the vapor density is given, it means the gases are non-reacting. That you have to assume. Because for reaction, we must have certain condition, right? So that condition is not there, right? So vapor density, if it is given, the gas is non-reactive, that you can take as it is. Mixture of this is 34.5. Calculate the composition of mixture in mole percent and mass percent. Find out this. Are you done? Okay. And what about by mole percent? Fifty-fifty. Yeah, right. Shitish, that's correct. See, I'm doing this. See, what we need to do, we have a mixture of NO2 and N2O4. So suppose we need to find out mole percent. So what I'm assuming X mole of NO2 we have and 100 minus X mole of N2O4. So X is nothing but the mole percent out of 100 is. Vapor density is given. So the molecular mass of the mixture is equals to 2 into Vd, and that would be 69. And this is equals to the total mass of this, that is, we can write mass of NO2 plus mass of N2O4, and this divided by the total number of moles, which we have assumed 100, right? Because X plus this is 100 only. Now this 69 is equals to mass of NO2 is what? Number of moles into molecular mass of NO2. What is the molecular mass of NO2? 46 plus 100 minus X. Molecular mass of N2O4 is 92 divided by 100. So you need to solve this. You'll get X as 50%. Okay. So mole percent of NO2 and N2O4 is 50. Clear? No doubt. All of you understood, guys? Hundred is the total number of moles. See, M average is what? Total mass by total number of moles. So this is total number of moles. Right, total number of moles, because that we have assumed. If total mole is 100 and out of 100 X mole is N2, so N2O4 is what? N2O4 is 100 minus X. This is what we have. So the molecular mass of the mixture is 69, and this we can equate with average mass, this total mass by total number of moles. Understood? I did not solve it step by step. You can solve this expression easily, you will get 50%. Tell me, did you get it? Did you get it, guys? Correct. So like this, we calculated mole percent. Similarly, we can find out mass percent also. So for mass percent, you can start afresh. We have a mixture of NO2 and N2O4. So there I have assumed number of moles. Here I assume total mass. So if I assume total mass of the mixture is 100, and out of that, suppose M is NO2, so 100 minus M is N2O4. So again, the average mass is 69 is equals to total mass is 100 divided by number of moles of NO2 plus number of moles of N2O4, which we can further simplify as 100 divided by number of moles of NO2 is M mass divided by molecular mass 46 plus 100 minus M divided by 92. So 69 is equals to this. When you solve this, you'll get the value of M. Did you get it? Tell me, did you understand this, all of you? Clear? Yes. But I won't recommend you to use this method for this question. This is the general way. With this method, you can solve all other questions. Now, another method is what? Like alternate method is what? You know the mole percent, right? You know the mole percent, that is 50-50%. And you know the molecular mass of NO2, which is 46, and the molecular mass of N2O4, which is 92. You see the molecular mass is exactly double. So to have equal mole percent of the two gases, we must have the mass of NO2 that we have here. It will be twice of the mass of NO2 is twice if the mass of N2O4 is M. Sorry, I have written it other way. Mass of NO2 is M. That would be half of the mass of N2O4, because the molecular mass of N2O4 is twice to that of NO2. So for the both gas to have equal number of moles, mass of N2O4 should also be twice to that of NO2. Yes or no? All of you, did you understand this? Please write CLR quickly. Did you understand this particular thing? I know you can do this by this method. That is not a big deal. You can do this. It's just a calculation. But I want you to understand this. Since the mass of N2O4 is 92 and this is 46, and this you can use for this question only. And that is why they have given this particular gases, so that you can do this calculation easily and save your time in the exam. If you use this method, you'll require more time to solve this, right? So it is 46, 92. Since the mass of N2O4 is twice to that of NO2, molecular mass, hence the mass of N2O4 should be twice to that of NO2 in order to have the equal number of moles, correct? So what is the percentage mass of NO2? Since we know this relation, the percentage mass of NO2 is what? M by total mass of this, M plus 2M into 100. That is 1 by 3 into 100, and which is 33.3%. Similarly, the percentage mass of N2O4, we can write 2M by M plus 2M into 100, or 100 minus this simply, 67.7% approximately. Did you understand this method, the second method? $66.7, correct. Is it right? Any doubt in this? No? Fine. Okay guys, so we'll take a break now. Okay, we'll be back at 6:50. Right? Take a break now. Okay. Response. Hello. Shall we start? Can you hear me? Okay. Okay, the next thing we have to discuss here is we call it as stoichiometry. What we are going to discuss in this portion is, suppose if I write one equation, okay, don't write this now, okay, just you see this, what is this? N2 gas plus 3H2 gas gives 2 NH3. Okay. Now, depending upon the number of moles of nitrogen and hydrogen, suppose we have taken different moles of it. For example, I have taken 2 moles of nitrogen and 6 moles of hydrogen. I have taken 3 moles of nitrogen, 9 moles of hydrogen, right? 3 moles of nitrogen, and 6 moles of hydrogen. One mole of, or suppose I have taken 2 moles of nitrogen and 8 moles of hydrogen. 4 different cases I have taken. 1, 2, 3, and 4. In all these 4 cases, we'll get what? We'll get different amounts of product here, ammonia. So here we need to find out that what is the amount of product we get in this 4 different conditions. Okay. Amount of product we get in this 4 different conditions. So how do we find out that? Because there are 2 different reactants, that is nitrogen and hydrogen. And if you look at the reaction is balanced here, right? And we can say 1 mole of nitrogen gives 2 mole of ammonia. 3 mole of hydrogen gives 2 moles of ammonia. That is what we can say. Yes. So depending upon the reactant, the amount of reactant, the product forms. If the reactant is very high, right, number of moles of reactant is very high, then the amount of product will also be more. If the reactant is less, the product will also be less. Okay. But which product on the basis of nitrogen or hydrogen will find out the product, or will take any one of the 2, right? Like suppose you see here this reaction, 3 moles gives 2 moles of NH3. So could you tell me how many moles of NH3 forms by 6 moles of H2? Could you tell me? In this reaction, suppose I'm taking 6 moles of H2. This 6 moles of H2 gives how many moles of NH3? 2, right? 3 gives 2, 1 gives 2 by 3, and 6 means goes 4, not 2. It's 4. 3 gives 2, so 6 gives 4, double, right? Could you tell me how many this 3 moles of nitrogen gives here? 3 gives 2, so 3 gives 2 moles of this. So point here is what? 6 moles of hydrogen gives 4 moles of NH3, and 3 moles of hydrogen gives 2 moles of NH3. So which one we should consider to find out the product amount of product here? Are you getting it? Hydrogen and nitrogen both are giving different amounts of product. So in this case, which one will consider to find out the amount of product forms? right? That is the question. Okay. See, Rubab, what I'm telling you that 3 moles of nitrogen give 6 moles of NH3. Yeah, that's right. That's right. 3 moles, 1 moles gives 2. Yeah, fine, fine. 1 mole gives 2, 3 moles gives 6. Right? Okay. One mole gives 2, so 3 moles gives 6. 3 moles gives 2, so 6 moles gives 4. That is right now. Nitrogen gives 6 moles of NH3. Hydrogen gives 4 moles of NH3. So which one we should consider? That is the question. Is it clear now? Right? So in this type, we can have mainly 2-3 types of question possible. Okay. One is when the reaction is complete, and one is when the reaction is incomplete. These 2 types of question there forms. Okay. In this 4 condition, could you tell me how many reactions are complete reactions? 2. The first 2, right? The first 2. Yes. Now in the first 2 reactions, since it is the complete reaction, so whether you take nitrogen or you take hydrogen, both gives equal amount of product. You can cross check this. What I'm telling you, in case of complete reaction, whatever reactant you are considering, you will get equal amount of product. You can cross check this. Here you will get 4 moles of NH3, whether you consider nitrogen or hydrogen. Here also you'll get 6 moles of NH3, whether you consider nitrogen or hydrogen. Yes or no, guys? Correct? Right. So in case of complete reaction, you don't have to worry about any one you consider, and then you can find out the product. That is one thing. But when the reaction is incomplete, then what we have to do? That is the question. Because both reactant gives different amounts of product. So we have to consider only one. Both we cannot say because the answer will be one here. So this is one kind of question you get, right? In which the reaction is given, reaction is known, we have balanced reaction, but different amounts of product, the reaction is incomplete. Okay? Reaction is given, complete, the balanced reaction is there, but reaction is incomplete. Another type of question is what? That the reaction itself is not given. Or if it is given, then you cannot balance the reaction. You do not know the reaction. What are the different products we get? Okay, the 2 types of problems we get into this. Complete reaction, you won't get any problem because it is very simple and straight. Okay, that is not the case we are going to understand. Okay, so basically in stoichiometry, what we are going to see here, that first of all, we have to discuss about here, write down in this, in this section, we'll study about the chemical reaction and the formation of product in a chemical reaction. We'll study about chemical reaction and the amount of product in a chemical reaction. Now, when you talk about chemical reaction, write down the next point. Chemical reaction is classified into 2 categories. Chemical reaction is classified into 2 categories. The first one, the balanced chemical equation or the balanced chemical reaction. And the second one is unbalanced chemical reaction. unbalanced chemical reaction. So in case of balanced chemical reaction, if you have to find out the amount of product forms, okay, so here what happens, we'll use the concept of limiting reagent. Limiting reagent. In short, we'll write it as LR. Right? In this case, since the reaction is balanced, okay, so in this case, the number of atoms constant both sides. Reactant side and product side, the number of atoms must be equal, then only it is balanced. Okay, but when we have unbalanced chemical reaction, we'll use principle of atomic conservation to find out the amount of product. We'll use the concept of, or the principle of atomic conservation. We call it as POAC in short. Principle of atomic conservation, POAC. Okay. Write down one more point here. In a balanced chemical reaction, the coefficient of reactant and product is called stoichiometric coefficient. Stoichiometric coefficient. Okay, stoichiometric coefficient. So we are going to deal with first balanced chemical reaction. Okay, what is limiting reagent? We'll see first. Write down limiting reagent. Achha, stoichiometric coefficient. Stoichiometric coefficient is this. Stoichiometric coefficient. Any doubt? No? Okay. So what is the limiting region? Write down. This is the reactant. This is the reactant which gets consumed completely. This is the reactant which gets consumed completely and produce minimum amount of product. Okay, this is the reactant which gets consumed completely and produce minimum amount of product. Now you see, I'm going to take the same example which I have written over there, right? N2 plus, we have N2 plus H2 gives NH3. Okay, so if the reaction is given, first of all, what we do, will balance the reactions. N2 plus 3H2 gives 2NH3. So this 1, 3, and 2 are the stoichiometric coefficient. Stoichiometric coefficient. Okay, this 1, 3, and 2, balanced chemical reaction. Now, what is the number of moles I have taken for the last two? 3 and 6, or 2 and 8. Okay, 3 and 6 and 2 or 8. So here we have 3 moles of N2 and 6 moles of H2. Reaction, obviously, you see, if the respective number of moles is not in the ratio of their stoichiometric coefficient, then the reaction won't be complete, right? Reaction will be complete reaction if the given number of moles must be in the ratio of their stoichiometric coefficient, right? Means this reaction will be a complete reaction if this is 3 and this is 9, right? If this is 10, this should be 30. If this is 100, this should be 300 moles. Means if the ratio is 1:3, which is the ratio of the stoichiometric coefficient, the reaction will be a complete reaction, right? And in that case, we'll get the same amount of product with respect to the all reactant. Like you see in these 3 cases, you can take any one of the reactant, you'll get the same amount of product. You can cross check. Okay, so for complete reaction, what is the condition we have now? Could you tell me? Condition for the complete reaction, that the reactant molecule must have their number of moles in the ratio of their stoichiometric coefficient. Did you get it? I didn't get you. Got on, Anusha? Understood? So this, we can take any number of moles, but if their ratio is 1:3, then the reaction will be complete. Any doubt, anyone? Please tell me fast. No? Right. Fine. Let it be. So if the ratio is 1:3, then you don't have to worry about any one you can consider, and that will be the case of complete reaction, and we can get the product easily. But in this case, which is the incomplete reaction here, so the two different reactant gives different amount of product. Incomplete reaction. So in this case, if you have to find out the amount of product forms, we have to first find out the limiting reagent. And once you got the limiting reagent, all calculation will be done on the basis of the limiting reagent. You do not have to think about the other reactant Just you need to think about the limiting reagent, right? Now, how to find out the limiting reagent? Limiting reagent, like I said, it is the one reactant, it is the one molecule. That's what I said. I have given you the definition. It is the reactant which gives the least amount of product on being consumed completely in the reaction. Like, for example, you see, for 3 moles of nitrogen, what should be the number of moles of hydrogen required for the complete conversion of this reactant into the product? For complete reaction, what is the amount of H2 required for 3 moles of nitrogen? We required 9 moles, but how many moles of H2 we have? How many moles of H2 we have? 6 only, right? It means what? When the reaction starts, right, this 6 moles gets consumed completely, right? So after some time, what happens? 1 mole of this nitrogen left, there is no H2 present, and what happens? 4 moles of NH3 forms in this. 4 moles of NH3 forms in this. I'll tell you how 4 moles, right? But the point is that this is what? This is not present now in the reaction vessel. In the reaction vessel, we still have 1 mole of N2 present, but there is no more H2, right? Hence, H2 is the limiting reagent. Once you get the limiting reagent, you just have to forget the other reactant, which is nitrogen. Here you can think it is not at all present. Now, all calculation will do according to the limiting reagent. Like you see, we can say 3 moles of hydrogen gives 2 moles of nitrogen. So 6 moles gives how many moles of NH3, not nitrogen. So 3 moles of hydrogen gives 2 moles of NH3. So 6 moles gives how much? The answer is 4 mole of NH3. Now you can ask me if you have any doubt. Tell me, any doubt? Right? So this is a simple reaction. So we can easily find out the limiting reagent into this, right? But how do we find out limiting reagent? I'll tell you. Okay. First of all, for this kind of question, 2 things must be given. One is reaction, balanced reaction you must have. If the reaction is not balanced, you can balance this also. Basically, the reaction will be given, which you can balance easily. With reaction, number of moles which is taken here, that is also given in the question, right? So 2 things are there. For limiting reagent concept, you need to apply. You must need the initial number of moles plus the reaction, balanced reaction. Is it clear? Now, how to find out limiting reagent here? The first one, write down method to find out the limiting reagent. Method to find out LR, limiting reagent. The first step is balance the chemical reaction. The first step is balance the chemical reaction. The second step is divide the given number of moles with respective stoichiometric coefficient. And the third one, the one which has the reactant, which has lower value is the limiting reagent. Did you understand this? Correct. So what we'll do here, you see, I'll just wipe this off and again I'll write down. See here what happens. Here what happens. You have 3 moles of nitrogen and 6 moles of hydrogen. So first of all, we'll balance the reaction. This is the given number of moles. Next step is what? We'll divide this 3 by the stoichiometric coefficient of nitrogen, which is 1, and 6 by the stoichiometric coefficient of hydrogen, which is 3. So this is 2, this is 3, this is the lower value, hence hydrogen is the limiting reagent. Any doubt? Yes, yes. The number of moles, initial number of moles will be given in the question. Reaction will be given in the question. You can balance that reaction easily. Clear? Once you get the limiting reagent, you'll find out the amount of product with respect to that only. You don't have to do anything with the other reactant molecule. Did you understand this? In doubt? Any doubt, guys? Please reply. Okay. Solve this question based on this. The question is, in a reaction it is given KClO3 converts into KCl plus O2. This is given. Calculate the mass of O2 produced if 298 gram of KCl forms. No, it's not. Atomic mass of potassium is 39. 192 gram is correct, Anusha. Very good. Yes, 192 is correct. Very good. Did you get it, Shitish? Try. Okay, see, I'm doing this. See, first of all, the reaction is given. The reaction is given, and the first step is what? The first step is we have only one reactant here, right? So directly we can do this without the use of the concept of this thing, the limiting reagent. What is given in the question? It is given that calculate the mass of O2 produced if the mass of KCl is 298 grams. So first of all, we'll balance this reaction. So the reaction is 2 moles of this, 2 moles of this, and it will be 3 moles of O2. That is the reaction. Now, we can understand this, that 2 moles of this gives 2 moles of this and 3 moles of O2. So we can find out the number of moles of KCl produced here, which is nothing but given mass 298 gram divided by molecular mass of this 39 for potassium, 35.5 for chlorine, which is approximately we get 35 into 2 is 70 plus 4 74.5 74.5 into 4, so we'll get 4 moles of this, correct? Right. So here what happens, if this forms 4 moles, so what is the moles of this will get, because the ratio is 2:3. So the number of moles of O2 is what? 3 by 2 into 4. That is 6 moles of O2 we get. In mass, if you convert this, 6 into 32, that will be 192 gram of oxygen produced. Did you get it? Any doubt? Okay. This one you see, there is a reaction given, x plus y plus z gives x3 y5 z6. Okay, this is given. Question is 5 mole of x gives 6 mole of y gives 10 mole of z, reacts to form the product, which is x3y5z6 product. You need to find out the limiting reagent, find LR, and the number of moles of product forms. Do this. Okay, so the limiting reagent is Y you are getting. Yeah, that's right, Ashish. Y is the limiting reagent. Correct, Oro? Shit is right. Correct, Pradyun. No, X and Z are not, Pradyun. It's Y. Check your calculation. It's not 1 mole. How it is X and Z? You see, the balance reaction is 3, 5, and 6. We are getting 5 moles of X. Okay. 5 of X, 6 of Y, and 10 of Z. So we need to compare what? We need to compare 5 by 3. We need to compare 6 by 5. We need to compare 6 by 5, and we need to compare 10 by 6. Okay. So in this one, which one gives the lower value, lowest value here? 5 into 6, 18. This is the lowest value. See, actually, when you have to compare this kind of ratio, no, 5 by 3 and 6 by 5, you can do one thing, because value you don't have to find out. You have to just compare which one is low, which one is more, right? So you just cross multiply this. 5 into 5 is 25. 6 into 3 is 18. It means this is lesser than this one. Since it is 18, it is 25. This is lesser than this. If you have to compare, suppose 6 by 5 and 10 by 6. So 6 into 6 is 36 this side, and 10 into 5 is 50. So this value is lower. It means 10 by 5 is more than 6 by 5. Any ratio you can compare like this. Suppose you have to compare 3 by 5. Sorry, you have to compare 3 by 4, 4 by 5, and 5 by 6. So 5 into 3, 15, 4 into 4, 16. So this one is, sorry, this one is greater than this. 6 into 4, 24, 5 into 5, 25. So this one is greater than this. This is the order. Did you get it? Right? So why is the limiting reagent here? Why is the limiting reagent? And then we'll do the calculation based on this. So 5 moles gives 1. So how many moles we have? 6 moles gives 6 by 5, and hence 1.2 mole of product we get here. Did you understand this? Yes. Okay, guys. So we are done with the session for today. Next class we'll start with the next thing, that is POAC, Principle of Atomic Conservation. Okay, and then we'll do some question, concentration term. Most probably next class we'll finish the first part of some basic concepts of chemistry. Okay. On Learning's assignment is already uploaded. Please solve those questions. Okay. Okay, guys. Thank you so much. We'll see you in the next class. Take care. Bye-bye. Yes, Shitish. All the questions, obviously, you cannot solve, but whatever you can do that. Okay, bye.